Hello and welcome to another lecture of Introduction to Astrophysical Fluids. In this lecture, we continue our discussion on the effect of rotation in astrophysics. Okay, so previously we discussed various aspects of fluid dynamics in a rotational frame of reference. We saw that how in a rotational frame of reference the Kelvin's vorticity theorem is modified, how the just due to Taylor-Proutzman theorem, a small obstacle at the very bottom of a liquid, okay, which is very slowly rotating, okay, can actually follow the motion about the obstacle even away from the obstacle that we saw. Okay, now in this lecture we will do something which are much more practical for our astrophysical interest. Okay, and that is nothing but the application of the application of this fluid dynamics, okay, in case of a self-gravitating body. And as you can easily understand, this is very much interesting and important for stars, okay, and the galaxies, okay, any self-gravitating stellar object. Okay, now one thing is there. Before starting, I am trying to mention that the analytical treatments are very much complex, so I will not go through every single step of analytical treatments. Okay, if necessary, I will tell you the details of the calculation. If I can, in some places I can tell you to check that at home as usual, okay, what I do in general in the lectures. But in some places, I will just tell you the results, and if you are interested, you can go through very good books by Chandrasekhar, for example, or by Bini and Treman. Okay, so you can see that. But for the scope of this course, what we are interested in are really the results of that. Okay, so the self-gravitating rotating mass is something which is of the central interest of our current discussion. Now the question is that how rotation affects the self-gravitating mass dynamics, okay, in general. And that is true because that is very important, because a star which is either in the main sequence or in the collapsing state, in both cases, okay, it rotates. So whether the collapsing is predominant or not, the effect of rotation can be very, very interesting to study, to know its effect on the evolution of a star or any other self-gravitating stellar object. Okay. Now it is true that in reality all the stars or stellar bodies which are collapsing under self-gravity are compressible in nature. That is true. But here, for our current analytical purpose, just for the sake of simplicity, we consider a self-gravitating fluid with constant density. Okay. So basically our density will be just a constant value. Okay. And we just think that the fluid is simply like a liquid. Okay. Now it is true that if the fluid does not rotate at all, then as the fluid is only under two forces, one is the pressure gradient force and another is the gravitational force, and the gravitational force is simply counterbalanced by the pressure force, okay, when we are talking about, of course, hydrostatics, just a very simple case. So in general we can think of there can be a spherical symmetry. Okay, just even if the fluid is in motion, just because the fluid is collapsing under gravitational field and the gravitational field has a radial symmetry, it's a central force, then we can think of a spherical symmetry if the fluid is not rotating. But if it rotates, then what happens to it? Okay. Now, what is the signature of being a rotating body? That means that the body should have some angular momentum associated with it. Okay. So, very intuitively speaking, from our everyday experience, we can say that there should be some flattening near the poles. Okay. So if you just imagine that, if you have seen how the potteries they are made, okay, that is also the same type of technology, right? They are actually rotated with a very high speed, and you will see that the central part gets flattened. Okay. So, and this there should be some flattening near the pole. Simply says that if you have, if you had previously this type of thing, now due to rotation, let's say around this type of axis. So in physics, whenever we talk about rotation, in astrophysics for example, mostly we will have a vertical axis of rotation, and then what happens due to this rotation, after sometimes the body will be flattening. Okay, so near the poles. So that is the meaning, okay, of flattening near the poles. So this body will then becomes oblate, okay, from sphere to oblate. We will see that. Now, of course, the thing is that, can we do something analytically at this point? For that, we have to consider that the fluid is not only incompressible but also is undergoing a solid body rotation. So you see that incompressibility and solid body rotation, these two together make our life simple and set for doing analytical things. So this is not a bad assumption for slowly rotating stars, as we have already discussed, but for moderately or quickly rotating stars, this is not a very good solution. Okay. Not a reasonable assumption, okay, not a valid assumption. So now the question is that, let's say we are in such a situation where solid body rotation can be approximated reasonably. Now, for those type of systems, it is actually possible to go to a reference frame, as we have seen in the previous lectures, where the frame is rotating with the same angular speed as that of the fluid, and so with respect to the frame, the fluid is simply at rest at all points. So we can simply say that with respect to the rotating frame of reference, the fluid velocity is 0 at every point. Okay. Now recall the fluid equation from a rotating frame of reference. The total equation, del V del T plus V dot nabla V is equal to minus gradient of P by rho. Although here just remember that rho is a constant, okay, because we are dealing with compressible fluids, minus gradient of phi, which is the true gravitational potential, minus half of modulus omega cross r whole square. Okay, this is the part which came from the centrifugal acceleration, and these two together creates phi effective. Okay, so not including the gradient, but these two is equal to phi effective, and plus we have the usual viscosity term and the Coriolis term. Now when V is 0, well, we don't care about those terms which identically vanish. Okay, and so we have only these two terms which are surviving. Okay. So with v is equal to 0, we simply have gradient of p by rho, because rho is now constant, plus phi minus half modulus omega cross r whole square is equal to 0. So the whole thing is a function of time. Okay. Or that can be a constant. But in general, there is nothing. So in our whole problem, there is nothing which can be a source of an explicit time dependence. So we simply say that this thing within the bracket is just a constant. Okay. So p by rho plus phi minus half modulus of omega cross r whole square is equal to a constant. Now, this is true for any at any point of the fluid. Now we are considering just the outer surface of the fluid, and we say that with respect to the interior of the fluid, the outer surface, which is at a pressure balance with the ambient, having a very small pressure, we can simply say that at the outer surface the pressure is 0. It's almost like if you have like a fluid like this, and you are saying that okay, the pressure inside the fluid, I mean in a liquid, okay, so it's a hydrostatic problem for a liquid. So the pressure increases with depth, so you can call this as P0, and here it will be P0 plus, you all know that, H rho G type of thing. Okay, so and now you can simply understand that when P0 is some arbitrary value, we can simply set that, so P0 is just a reference, we can set that as 0. So we can simply say that P is 0 at the outer surface, and for the outer surface only this part is constant because P is 0. That is true only for the outer surface. And in addition, if we also assume that z axis to be the axis of rotation, that means we take something like this. So this is the x-axis, this is the x-axis, y-axis and z-axis, and we say that rotation is around this axis. Then you just calculate this one. So this is a small home task you can do. Okay, and you will see that this is equal to constant is simply reduced to phi minus half omega square x square plus y square is equal to constant. But this is true only for the outer surface where P is equal to 0. Okay. Now, experiments show that an incompressible fluid sphere, okay, becomes ellipsoid under rotation. Also, you can do that in simulations. Okay, but this is also very much, intuitive. Maybe from some, as I said, in a pottery farm, you can see this type of thing. Okay, so from that you can, of course, in pottery farm you have a soil cluster type of thing, but not this. But you can actually see that something which is initially like this or which is initially like this, actually with time they gets flattened. Okay, they gets a bit ellipsoid. Okay, so that is simply because of the centrifugal force. That is very intuitive. Okay, so now in this analytical treatment, what we will try to do, we will simply assume that due to the rotation, okay, the incompressible mass sphere actually becomes an ellipse with equation x square by a square plus y square by b square plus z square by c square is equal to 1. Okay, and that is for the boundary surface. Okay, and we will simply check that finally where we will go should be self-consistent with this assumption or not. Okay. Now the question is that if we assume already that this should be the shape, this should be the shape of the surface of the fluid under rotation, okay, when the fluid is incompressible, then we can be interested to know the potential or the gravitational potential, okay, at any point inside the ellipsoid. So the gravitational potential inside the ellipsoid, okay, because if we can know that, then we can actually find the value of this gravitational potential at every point on the surface as well, and then mixing all this information we will do something very interesting. But at first we have to just check for the potential function at any arbitrary point inside and also the surface of the ellipsoid, and this is given by this expression phi is equal to pi g rho, okay, times alpha 0 x square plus beta 0 y square plus gamma 0 z square minus chi 0, where alpha 0, beta 0, gamma 0 and chi 0 all can be expressed in terms of ABC, but there is an integration over the so-called Lagrange multiplier. I am not going into the detail of the process, just to tell you that only when you can integrate, then only, successfully integrate and make the expressions out of, free of the multiplier, then each of these alpha 0, beta 0, gamma 0 and chi 0 will be expressible purely in terms of A, B and C. Okay. So now the question is whether under the given surface situation, surface constraint, we can integrate that or not. Okay. So one thing we can do, so that question we will try to solve a little while later, okay, after some time, of course. Okay, so now what we will do, so we now have this expression for phi, and we also know that this phi in 3 we can replace in 1. Now if you were interested to see, this is 1, but if we replace that in 1, then that will be the phi only at the surface. So we can do that. So we have done here this, and we will see that at the outer surface, okay, we have this constraint equation which simply says that alpha 0 minus capital omega square by 2 pi g rho times x square plus beta 0 minus omega square by 2 pi g rho y square plus gamma 0 z square is equal to some constant. Okay, so this is only valid for the outer surface, and this is also the equation of the outer surface. Okay, now we have now 2 and 4, so this one and this one. Okay, so both, so if we just take this equation, so this simply gives us the this simply gives us the the equation of the surface and not any point inside, okay, or outside, because inside or outside, that should be an inequality. Okay, the equality is only on the ellipse, surface of the ellipsoid. Okay, now if two equations are both true for the surface of the ellipsoid, same ellipsoid, then we can simply say that their coefficients will have, their coefficients will carry the same proportion. Okay, so if this is true, then we can simply write, this is a small home task, again you can do at home, that if both 2 and 4 are valid, then one can write that the coefficient of x square, which is 1 by a square, okay, and divided by this coefficient will be equal to, or actually we have to say, because in the right hand side there is 1, so we have to make this constant to be some k0, and then we have to multiply, divide the whole thing by k0. Okay, and then we just again take the ratio, and finally, so the ratio of the coefficient of x square, y square and z square. Okay, so we'll have the so the coefficients of x square, y square and z square, when they're divided by the coefficients of here, the of x square and y square and z square respectively, that means 1 by a square. Here that will be by 1 by b square, and here that will be by 1 by c square. Okay, so finally, and if you just then cancel out the whole k0, which is the constant over here, you will finally see that you have this relation: alpha 0 minus omega square by 2 pi g rho square times a square, because this by 1 by a square just gets multiplied with this. Similarly, that will be exactly equal to b0 minus omega square by 2 pi g rho times b square, which is the ratio of the coefficients of y square. Similarly, this will be equal to gamma 0 c square, that is the ratio of the coefficients of z square, and those three should be equal. Now if we finally solve this equation, just again by solving the integration involving the Lagrange multipliers, then we can express alpha 0, beta 0 and gamma 0 free of Lagrange multipliers, and then we are actually done. And what to do for this? So basically one can directly search for this, but this is an extremely complicated job. So people, they started to think that, okay, if we start with different type of geometry, okay, and so some geometries we can actually see already observationally or numerically. So from that we can propose some specific geometry, and we will see that whether solutions exist for that geometry or not. So for example, the first one is, if we just assume that the fluid has a configurational symmetry around its axis of rotation. That means if this is the axis of rotation, then perpendicular to this, every cross section is a perfect sphere. So this body, if it has 3 axes, okay, then the 2 axes, okay, then the 2 axes perpendicular to the axis of rotation, which is this one, will always have the same length, because this will be a sphere. Okay, so this type of geometrical shape is called a spheroid. Now spheroid can be elongated in this direction and contracted in this direction, or it can be elongated in this direction and contracted in this direction. Okay, so if this is like this one, which is not of our case, is called a prolate spheroid. If this is this type of thing, which is of our principal interest, is called an oblate spheroid. Okay, so for oblate spheroid, we can simply say A is equal to B. This is nothing but the 3 so there are not like major, semi-major axis or semi-minor axis. So this is semi-major axis, so this is the so-called semi-minor axis in this case, and the 2 major axes are possible, and these 2 major axes are exactly equal, that is A is equal to B, and the semi-minor axis C, which is less than both A and B, okay, is not equal to the A and B, of course, because this is smaller than both A and B. Okay, so this is the case. For proloid spheroid, what happens, for example, if you have a proloid spheroid like this, then it can have, not like this, but the proloid spheroid can happen only when you have I don't know, like rotation, this type of rotation. Okay, so which is perpendicular, which is in the horizontal direction, then you have this. Okay, but then you have circles like this. Okay, then this axis will be semi-major axis. Okay, and in a prolate spheroid, if you just assume that you have spheres like that, then actually the simple condition will be A is equal to B, but that will be less than C. So C will be the semi-major axis, and which will be greater than the two semi-minor axis. This type of thing. Okay. But for our case, we have this condition, and the corresponding eccentricity is E square is equal to 1 minus C square by A square. It is your home task. I have deliberately not written this. If A is not equal to B, then just find what will be the eccentricity of an ellipsoid. And if A is equal to B, then show that this reduces to this one. Okay. So, I mean, actually, in case of this, you can simply write this B square. So 1 minus C square by B square, because A is equal to B. Now, a solution for this type of spheroid was first found long time ago, 1740, by Maclaurin. Okay, so that's why this spheroids are known as Maclaurin spheroids. Okay, so you see the problem was treated. I mean, the problem is a pretty old problem. Okay, so now for the current case, what happens that actually one can integrate, and finally one can find the values of alpha 0, beta 0 and gamma 0 free of the Lagrange multipliers, and you can now see that both alpha 0 and beta 0 will be equal, and will be simply equal to 1 minus E square whole to the power half by E cube sine inverse E minus 1 minus E square by E square. So E is nothing but a function of C and A. So basically the final message is that both alpha and beta, alpha 0 and beta 0, they are expressible in terms of A, B, C. Here only A and C, we are just, for simplicity, we are just forgetting B, because B is exactly equal to A. Now, what about gamma 0? So gamma 0 will also be expressed in terms of E, which is in terms of C and A only. So gamma 0 is also expressed being independent of the Lagrange multiplier. Okay, so finally we have three things. So this is simply the indication that this is a this is a, how to say, a valid, this is a valid solution, okay, for the problem. Now if we put the expressions of alpha 0, beta 0 and gamma 0 in equation 5, what was equation 5? Can you remember this one? Okay, if we put that, okay, finally we have to see that what will be the gamma to, what will be the epsilon to omega ratio. For that we can finally, we can finally get such type of spheroids. Okay, so spheroid is possible, that is okay, but spheroids of which eccentricity is possible, that is not clear. And if we write then the alpha 0, beta 0 and gamma 0 in terms of their expressions, in terms of the eccentricity, then finally we can get a simple relation, comparatively simple relation between omega and E. Of course, analytically you cannot solve that very easily, but you can do something like numerically. Okay, analytically you can try, and you can get some plots like this. So this is, along the y-axis you have omega square by pi 0, which is plotted. So pi 0 is nothing but a constant, so omega 0, so this is just to make these things dimensionless. So omega square is plotted as a function of E. Now this starts from origin, that says that when E is 0, omega square is nothing but 0. So it simply says that E is 0 means C is equal to A, so which is nothing but a perfect sphere. So a perfect sphere basically indicates no rotation, and which is completely following our intuition. Now then, with the rotation, the eccentricity increases. but it doesn't increase indefinitely or limitlessly. When eccentricity, sorry, what I meant to say is that with the increase in eccentricity, okay, this omega also increases, but this omega does not increase limitlessly. Okay, when eccentricity first increases, omega increases up to a value of, so up to a value where omega square by pi 0 reaches 0.449, and that corresponds to an eccentricity, critical eccentricity of 0.93. After that, okay, after that, if eccentricity increases, omega actually decreases. Now, why is that? So that simply says that I mean, the much rotation actually causing it is simply saying that the small rotation actually is causing much efficient flattening after some point. Well, for that we have to actually take a look at the angular momentum and how it changes with eccentricity, for example, or how it changes actually with omega. Okay. So the moment of inertia of a spheroid of mass m and equatorial radius a is nothing but 2 by 5 m square capital omega, and which we call as L. Okay. Now the mass of the spheroid will be nothing but 4/3 pi a square times c. This is abc in general for an ellipsoid, but here it is simply a is equal to b, so a square c times rho, and then we just replace c in terms of a, so we have finally this 4/3 pi a cube 1 minus e square whole to the half times rho. Once again, in our whole analysis, rho is nothing but a constant. So after some lengthy algebra, one can show this dimensionless angular momentum. Once again, we made it dimensionless by dividing the true angular momentum by this factor. You check it, why it is a, you just check it that this has a dimension of angular momentum. Okay, if we do that, we can see that this dimensionless angular momentum is related to the angular velocity like this. So using equation 6, this one, we can now find a relation between L and, or rather L dash, L prime, no, what is that? L bar with the eccentricity E. And again, we have to solve numerically, and what we can actually see is that this is the typical behavior of L bar or L bar as a function of E, and you will see that first it increases and finally it saturates to some value when E reaches 1. So now what happens? So for L, this always increases. So with eccentricity, L is always increasing. Okay, but what happens? L is increasing, but this L is increasing not in a, L is increasing in such a manner that I is increasing. That means the moment of inertia is increasing, but this omega is no longer increasing. Okay, but the product is actually increasing. That is possible because finally L is a product of I and omega. So I is increasing, omega is not increasing that much. So but the product is increasing. So, and simply that is the meaning that, so finally it is true that although it may be paradoxical that omega is getting down, so that means that whether the effect of rotation is getting down, no, that is not true, because I is actually getting up, so that the effect of rotation, which is not actually given by omega but it is given by L, okay, is actually enhanced with enhanced eccentricity. Okay, so that was the like explanation for the previous plot. So in this part we saw something called the spheroidal geometry. Okay, spheroidal shape of a self-gravitating mass under under rotation. Now the second possibility is Jacobi ellipsoid. So there is another possibility where A is not equal to B, not equal to C. That is also possible. And in the year 1834, okay, so he was in 1740, okay, and it was in 1834, almost, okay, 94 years later, almost 100 years, okay, Jacobi established the surprising fact that equation 5 also permits, under certain circumstances, ellipsoidal solutions as well. That means, once again, that means we can solve efficiently the integrals so that we can express all these alpha 0, beta 0 and gamma 0 irrespective of the Lagrange multipliers in terms of A, B and C. And in that case, finally the constant comes out. I am not going into the mathematical details, just for your information. The constant comes out to be alpha 0 minus beta 0 times a square b square plus gamma 0 c square times a square minus b square is equal to 0. Okay. Now, so this is exactly the constant what we can we can have for a Jacobi ellipsoid. And from that, just following the same type of methodology, you can check the dependence of omega with respect to, I mean, omega as a function of the eccentricity, and also the angular momentum as a function of eccentricity. And it is actually seen that by extensive analysis that when this non-dimensional angular momentum L bar is greater than 0.304, then only Jacobi ellipsoid is possible. If L is less than 0.304, the only possible geometry is the Maclaurin spheroids. Okay, so here you can actually see that we have very briefly discussed the outline of two type of geometrical possibilities of the shapes of self-gravitating fluid masses, of course incompressible and solid rotating, right, uniformly rotating fluid masses under rotation. But the true problem, of course, lies in the treatment of the whole things in a compressible framework, considering the differential rotations. Some of those things will be qualitatively discussed in the next lecture. Okay, thank you very much.